Hi there, we want to graph this function using transformations. F of x equals negative 1 over x plus 5. So first we want to identify the parent function. So if you were to strip away all of the numerical values, so in this case, you would be taking away the positive 5 and the negative 1 that's multiplied out in front, you'd be left with y equals 1 over x. So y equals 1 over x is my parent. And that is the reciprocal function. And to graph this by hand without our calculator, we really have to know what the reciprocal function looks like. So I'll get to that in just a second. Now we have two different transformations that have occurred here. Our first transformation is from this negative 1 that's multiplied by the 1 over x. So that negative 1 is going to cause a reflection, and that is going to be a reflection over the x-axis. So we're going to start by reflecting over the x-axis. And then we have a second transformation that comes from the plus 5, and that's going to be a vertical shift. So that's going to be a shift up 5. So once we have determined our transformations, we want to think about the parent function, y equals 1 over x, and I'm just going to think about what that graph looks like. So hopefully you get to the point where you've done enough of these that you have a visual picture in your head. You might not have to actually draw it out on paper, but you can think about what the function y equals 1 over x looks like, and you already have that visual. If not, then you go ahead and think about if I were to substitute in x equals 1, I'd have 1 divided by 1. That would be the coordinate 1, 1. If I substitute in 2, that will give me 1/2. If I substitute in 3, then I get 1/3. So I start to see these y values get smaller and approach 0. However, if I substitute in 1/2, then I have 1 divided by 1/2, which gives me a larger output. That would give me an output of positive 2. And if I substitute in, for example, 1/3, then I get that positive output of 3. So what happens is my y values actually are going to get bigger here as my x values get closer to 0. And then 1 over x is an odd function, so it has that origin symmetry. If I substitute in negative 1, I get a negative output. So we have the symmetry across the origin for the parent function 1 over x. So that's what my basic parent function looks like, and I'm going to use that to help me build the graph of f of x that I was given. Now notice on that parent function y equals 1 over x, it has a vertical asymptote here, and that vertical asymptote is the vertical line x equals 0. So when I look at the two transformations reflecting over the x-axis and shifting up 5, neither of those transformations is going to change the vertical asymptote. So I'm going to go ahead and graph in my vertical asymptote. It is going to stay x equals 0. And I always recommend that you graph these on graph paper, and I like to use a highlighter for the asymptotes. So there's my vertical asymptote, x equals 0. Now my horizontal asymptote on the parent function is the horizontal line y equals 0. However, when I look at my transformations, if I move up 5, then this asymptote also moves up 5. So I'm going to graph my horizontal asymptote, but it's not y equals 0 anymore. Now it's y equals 5. And remember, I'm graphing the asymptotes as dotted lines because they're like guidelines. The graph is going to get really, really close to those asymptotes, but the graph is not actually going to intersect these asymptotes. So this asymptote is the horizontal line y equals 5. All right, so next I am going to take a look at some points that are going to be on the graph of f of x. So if I look back to the graph of y equals 1 over x, when I plugged in 1, I got an output of 1. And when I plugged in negative 1, I got an output of negative 1. And notice these 2 points. we talked about the origin symmetry and how close they are to the origin. So from the origin, I basically went up one and right one, and then I went left one and down one to get to these 2 points. I call these points my anchor points because I'm going to find that I have similar points on the graph of my new function. However, if I were to reflect these points across the x-axis, then the point that used to be at 1, 1 is going to be down here at 1, negative 1. And the other point that was at negative 1, negative 1 will go up and be here at negative 1, positive 1. So I'm thinking about where those anchor points are going to go if we do a reflection. And then I'm also going to be shifting those points up 5. So looking at my new graph, it's as if my origin was shifted. So I'm looking at like this point here, like this is my new origin. And I'm going to think about where my anchor points are located with respect to this new origin. So from that new origin, I'm basically going to be going left one, up one. I'm going to get that anchor point right there. And then from that new origin, I am going to be going right one, down one. And this should make sense because if we do a reflection over the x-axis, then instead of my branches being up in the first quadrant and the third quadrants, I'm then reflecting, so now my branches are going to end up being in the second quadrants and fourth quadrants. So that's kind of how I figure out where my anchor points, what I like to call the anchor points, are located. But in addition to those points, we can also, of course, find the X and Y intercepts, and those can be additional points that we can graph on the function. So let's do the y-intercept next. And we know for any function, when we're trying to find the y-intercept, we are always going to let x equal 0. So now we're talking about the original function. So we're finding f of 0. And let's see what happens when we substitute 0 into the original function. Negative 1 divided by 0 plus 5. And we notice that this is going to give us an output that is undefined. This does not exist. So that means that we have no y-intercept. The graph is not going to cross the y-axis. And if we look at our graph, that should make sense because notice we had a vertical asymptote right here of x equals 0. So there's no way we were going to be able to cross the y-axis because that happened to be an asymptote. So next, let's find the x-intercept. And to find the x-intercept, we're going to let y equals 0 this time. So remember, the original function, f of x, which was negative 1 divided by x plus 5, f of x is really our y value, or output. So this will be 0 equals negative 1 divided by x plus 5, and then we have to solve this equation. So we'll subtract 5 from both sides. Negative 5 equals negative 1 divided by x. Then I'll multiply both sides by x to undo this division. Negative 5 times x is negative 5x equals negative 1, and then divide finally by negative 5. And that will give us x is equal to 1/5. So my x-intercept is the coordinate 1/5, comma 0. And that will be another point that I can plot. That will kind of help me check to see if what I have so far makes sense. So if you plot the point 1/5, 0, that's going to be approximately right about here. Hopefully that location makes sense because looking at the parent function, we expect to have branches in the second and fourth quadrants roughly. So think about the anchor point then is going to pass through that x-intercept and hug the vertical asymptote, and then it's going to curve around like the parent function did and then hug the horizontal asymptote. And then the same will happen with the other anchor point that I had graphed. So we end up with 2 branches. Remember, the shape of this graph is identical to the shape of the parent function, except for it's been reflected over that x-axis and shifted up 5. So the whole idea is we're trying to use what the parent function looks like to help us generate the graph of this new function. And then the only other thing that you may be asked to find might be the domain and range. So I'll finish with that, and I'll just sneak those right here. So my domain is all the possible x values, and we said that x cannot equal 0, but x could be any other value. So my domain will be all of the x values from -infinity to 0. Get some more room. Union 0 to infinity. That's how we would write all values except for 0. And then the range, which is all of the possible y values. Now notice, let me trace this graph for a second. This graph goes down forever, so we're going to have from -infinity, and this graph comes up. But notice it never crosses that horizontal asymptote at y equals 5, and then it picks up again above the asymptote and then goes back up to +infinity. So it skips over the y value of 5. Therefore, our range will be from -infinity to 5, all values except for 5, and then from 5 to infinity.